Thank you everybody for coming. So have you ever played these freemium games? You know, those are those games where you have to pay in order to make it slightly more fun. So in these situations, I sometimes played, but I always resisted paying. In these situations, what happens is that there is some psychological mechanism. Well, they kind of try to apply to your psychological mechanisms to make you pay more and more. And this is connected with your inclination to gamble, but also also to kind of invest more of your skills. Because usually in these games, you do something, and when you pay more for another round, you also gamble, but you also have some chance to win if you're skillful. So imagine such a situation in experimental science. You start some experiment, it's not really working, but maybe you can save it, so you just continue investing in this experiment, both your time and your resources. On the other hand, this comes because of some properties of our cognition. So usually this is called kind of principle of consistency. We usually try to be consistent and committed to ideas that we already invested in, and also that we expect from us to be capable of doing, and others expect from us that we are capable of doing them. So there is both personal and interpersonal pressure to do it. And well, we also, so there is another phenomenon slightly different of cognitive dissonance, where we don't want anything in our mind that is not that is conflicting with our core belief system. We have to take in mind all these nice illustrations when we think of experimental science, because when we do this science policy, social epistemology of science, we are focusing on maximizing scientific knowledge as a whole. And we are trying to think how to optimize resources, distribution of resources. When we do that, we can kind of, what already previous two speakers were mentioning, we can also do this from the top. So, for instance, from perspective of some funding agency, or from perspective of someone who creates scientific policy, who kind of estimates how much certain research will be valued, which impact will it have. These simple traps in personal, in individual psychology can also be seen in a group. So I assume most of us here knows about Anderson's story of the emperor and his clothes. His new clothes, when nobody was willing, first of all, so there are two components. Nobody was willing to say to the emperor that he is actually naked, because they were thinking that they might be wrong, because everybody else behaves as if he is fully dressed. On the other hand, he was also some sort of authority. So they were also scared of his authority maybe, and did not express what's actually going on. Such situations we can also have in scientific environment. And actually, it might often be very reasonable to listen to authority in the sense of expertise, but on the other hand, maybe having more diversification of ideas and just expressing your own opinion can be beneficial. So what is so special about these groups? Here in this picture up, you can see my friends discussing after a seminar, and they're sharing their ideas, what's going on, and something new might come. Why is that? Because knowledge is something special. It's not like running. So when some professional athlete runs, he will always run faster than some big group of professional athletes. But the knowledge, the logic says that our virtual knowledge that all of the members of the group have, is always higher, so of the group of experts, is always higher than individual knowledge of a single expert. there is a big question how to aggregate this knowledge. So then we might, if we aggregate it in a wrong way, we might end up with something that is suboptimal. Then we are thinking how to do that. On the other hand, there are a lot of very specific debates, concrete problems of concrete laboratories, how to structure structure the resources, how many members is the best to have. And for instance, some research points out, in biology we also show that maybe we hopefully have some conjectures about physics, high energy physics, that in certain aspects, very data dependent aspects, smaller groups might be more efficient. This is not, of course, always the case, but it sometimes is. We will come back to that later in the presentation, but I hope this all persuaded you that this switch from the traditional epistemology focusing on a single agent to this social epistemology that has a goal of optimizing knowledge of the whole group is something worth pursuing. Then we can have very good general arguments for these claims, but sometimes we also want to know answers to very particular data-dependent questions. So when we are asking what is the optimal number of a researcher within a specific team, you can get very, very different answers. So some research pointed out in psychology, actually, and they did focus on teams in psychology, so they just gave some numbers, 12, 7, and so on, but this is very data dependent. You cannot apply this to any research team in any possible context. Another conjecture was that, or a result, was that there is a curvilinear relationship between the team size and its performance. What does this mean? Well, this means that increasing the team size is beneficial up to a certain point, and after this point, it actually, then the team actually underperforms. So it just gets, there is some saturation point after which we should not increase the team members. But to do some data, to answer these data-dependent questions, we really have to have these data repositories. We really have to have a lot of data that we can later relate to, that we can analyze. In order, when we think of, so which type of data is this? Well, this should be something that I called external experimental data. On the one hand, we have internal experimental data, which are experimental assumptions and the results, both positive and negative, of a particular experiment. On the other hand, funding agencies often collect what I call external experimental data. These are purely numerical data, numerically expressed inputs. And numerically expressed resources used for this experiment. Of course, it's clear that there is an interplay between these two types of data, but this is just to motivate the importance of collecting these external ones, this purely numerical data, which is collected, but it's usually not publicly available. So who collects it? Well, the big funding agencies collect it. Here we have example, the Dutch funding agency for science, German one, European one, but they unfortunately don't make it available and systematized. There is one positive example, and this is Inspire directory for high energy physics, this directory takes data from more than one high energy physics laboratory, but particularly good one is the particularly useful and exhaustive are data that come from Fermilab. So Fermilab somehow recognized the importance actually to make publicly available and to systematize these external experimental data that they have. What do they show us? Well, what's available? A list of all projects proposed. So you can also see the projects which were rejected. You can see dates when they started and when they ended. Actually, when they proposed it, how long it took until they get approved or rejected, and then if they were approved, how long they lasted. You can also see whether they're linked to some other experiment. So whether some other experiment was some sort of continuation of the first experiment. Second of all, you can of course see the list of proposing authors, and in a way you can also see how these authors were teamed. In a sense, you can see from which institutions they are coming. All these things we can use as some sort of inputs. On the other hand, what we can use as an output is the number of citation per paper. So here you can see some example. Well, unfortunately, it's not overly big. Is it better? Okay. So basically, you can see every proposal has its own number. Then you can see dates proposed, approved, and so on. These numbers, then you can see that they really deal with this citation in detail. So they kind of list all the... yes, they also show you whether the Fermilab had lead in these experiments or not, and so on. They list these citation, the total number of them, but then also they rank them. So based on the number of citation, they classify some contribution of an experiment, some paper that is a result of this experiment as very well known or renowned, and this depends on the number of citations. And there were disputes actually. What is this number of citation? How do you come with it? And physicists were actually thinking that this is kind of meaningful and important to discuss, and that this is discipline dependent. So not in each discipline these numbers will be the same. So we really talk about data dependent situations specific for each context that we have. When we evaluate this repository of Fermilab, we can see that it's online, it's open, it's free, so it's transparent. That's very, very good. Their data are extensive. They're also structured in some way. So on the negative side, this structure of the team with respect to seniority, so what is the ratio between senior and junior researchers, is omitted. Though you can somehow infer it, because they actually, Inspire actually has this idea that each physicist has to have his own personal data linked to his name, so that you can actually see when this person finished his PhD, started important projects, and so on. So you can somehow classify it. Unfortunately, this is not done for every person, so not every person is in the system. But the general idea is there, so also to include that. And the last point is there are no funding details for older experiments. For the newer experiments, they now started also including funding details, which is also a positive aspects. But we cannot really focus too much on the newest experiments because we still cannot estimate their impact, or it's not so straightforward to do it. In the next part of the presentation, I will point out three key policy-making questions, potential problems for these questions from the internal perspective, and how we can solve. Well, I will give some suggestions how these external approaches can be useful, and by this I will consider quantitative methods on external data gathered. Of course, have in mind that these potential problems will only be some sort of psychological puzzles, so this is not something that we really this is not something that was tested in a scientific environment. So they exist as a general phenomenon. In economics, you can also see this research, in psychology. But I think it would be beneficial if at least some of these tests are done, particularly in scientific community. So these 3 questions: how to structure a research group, how much funding to invest in an experiment, and when to end an experiment when it's unsuccessful. Sounds simple, but it's actually extremely complicated. So, yes, what could be a potential problem when structuring a research group? One of the potential problems is that researchers, if you have too many junior researchers and only 1 or 2 senior researchers, they will most likely, so that of course has to be tested, but in other situations it's really clear that we do comply with authority, we trust experts more, and this is also a very rational strategy. Usually experts are right. Unfortunately, it might destroy diversity within a research group, so it might not be the most rational thing to do. It might not be the optimal way of when structuring a research group. Another problem is a problem of information cascades. So you probably saw sometimes 2 bars, one across the other, one is packed, another one is half empty, and you wondered, okay, why one is so packed and another one is empty? Is there some big difference between them? And in some cases there is no big difference. So the prices are similar, the food they serve is similar, but we tend to go to the one which is more crowded, because we believe that when there are more people inside, we trust their judgment, which actually might not be completely rational. I can give you another example. Price of a book online. One bookstore by accident posted a price of one book that was very high, but then the other bookstore realized, oh, but they really raised their price of this book, we have to do the same. So they also raised their price, but nobody was actually buying this book. So the value of this book was actually not that high. So it was clearly irrational behavior. And this, in science, what can happen is that researchers all follow one approach, one research approach, because it's modern, because they're maybe not considering the other one. All the authorities, or just some few people started following the first one, and then it kind of catched up. So everybody ends up in this information cascade. There are some general arguments about how to optimize research groups, and from the quantitative perspective. So this is Professor Zollman's analysis, the famous one with a cycle wheel and a complete graph, where you see certain trade-off between connectivity and reliability of results, also the time to reach the consensus. And this is well, first of all, what we have to note, this is a hypothesis-driven simulation. By this, I mean that it did not have in mind some particular scenario. It was not fed by some particular data, but it's a general argument in this sense. It's a pioneering approach, one of the first actually simulations in social epistemology of science, and it was a quantitative result. Now, if we want to know some specific question, what is the optimal number of researchers within a team? What should be the ratio between senior and junior researchers? What is the optimal number of teams? Which also makes sense. We need something which is data-driven. So what can we do? Well, we can make some statistical analysis of seniority ratio of efficient projects, but first of all, we would like to know which projects are efficient. So one of the candidates to establish efficiency in taking account all the inputs and all the outputs is data envelopment analysis, which we did here in Belgrade. So Professor Perovic, Sandra Radovanovic sitting there, Andrea and me. So we will come shortly to that. And then there is another suggestion coming from Sandro, what in addition could be done, that we could kind of feed this statistical ratio of seniority inside a data envelopment analysis, and then have a network data envelopment analysis, which will take into account the structure of parameters, and then have something new as a result. But these are illustrations what can be done when you have this data gathered by Fermilab, because we actually use this Fermilab data that I showed you in the beginning. So data envelopment analysis is a very powerful tool. It's used to determining efficient systems. It optimizes over all inputs and all outputs, which is the best, I think the biggest advantage of it. But it requires a large amount of data. So it really requires data systematized in repositories, or someone really to collect big number of data and then systematize it. So what were the results? This is just a flavor of what we did. So what can you expect from such a data-driven simulation? Well, some results that we, for instance, got was the number of efficient and inefficient experiments. We also noticed that efficient experiments were the ones that were small with respect to teams, usually not more than 2, and inefficient experiments were much bigger, so 6 to 11 teams. And one assumption, one hypothesis why this could be the case, because you need to coordinate bigger teams. When you try to coordinate bigger teams, then it's like juggling. There are a lot of balls involved, so it's harder. So that there are more mistakes. Of course, you have to keep in mind that for some experiments, it's absolutely essential to have big groups, because you cannot perform them in small groups. Another key question that deserves an answer and consideration is how much funding to invest in an experiment. So what can be a potential problem? Well, we tend to link, this is psychological disposition, something expensive to superior, and to link something inexpensive to inferior. Also brands play, you can see this, brands play a very important role. You can have the same product by 2 different brands. Brand is really important, it's more expensive, it's a matter of prestige. So that's one problem. So, but on the other side, so when you do science, sometimes it actually makes sense to use expensive technologies because they are the cutting edge science. So that's exactly what you want to test, the best technologies, the best equipment that you can get. And also sometimes equipment is simply really expensive, so you just cannot avoid it. What you want to know is how to balance this, how to find the optimum between something that's actually really important to employ the newest technologies and what you actually need, because maybe you don't need all of these resources available and so on. So what is the best from this perspective? The point is, in order to do that, you would really have to have funding data available. After that, so this is something that we are considering. Okay, so when you have funding data available, you can just also use it as your outputs in data envelopment analysis. On the other hand, you can do maybe something different. So you don't have this available, but we can also estimate, we have some impression how much certain equipment is valuable, how much it had to be invested in it. Also, we can see the number of teams. So it's clear that if a team is bigger, more funding was invested. Well, usually, right? It's not straightforward, but that's... So we have to do some qualitative analysis of experiments. And then we can, after establishing that, we can do quantitative analysis, comparative quantitative analysis of the project that had similar results but different resources. And these resources somehow actually also point out that funding of ones were higher and of the others lower. Unfortunately, unfortunately, funding data is collected all the time, but it's not available, or in a lot of cases, it's not available. When I say this, I also checked European Research Council website and the data that they have on experiments. So you can be lucky. Some experiments by themselves put a lot of data because they're linked, but it's kind of arbitrary will how much a certain researcher wants to expose of his data. So it's not really organized and required, but it's definitely collected. So they definitely have to fill in all these forms and so on, so it's known. The last question is when to stop, when to end an unsuccessful experiment. And this brings us to the problem of the beginning of the lecture. So the principle of commitment and consistency has been first discovered in the 70s, early 70s. A psychologist experimented and got the results that people that on a horse bet, betting on horse races, that people believed much stronger that one horse will win once they bet on him. So once they invested something, then their certainty increased. So then they believed they must be right. So when we make a choice, in that sense we take a stand, then we have both personal and interpersonal pressure to behave consistently with this commitment that we made. In science, this can happen. It's of course, this debate is open, and I mean, there is a lot of research done in this. But what can this external perspective, external quantitative perspective bring to the table in this discussion? Well, it can tell, you can, after conducting data envelopment analysis, for instance, notice what is the efficient time of running an experiment. And you can also compare efficient with inefficient experiments. And then you see that, well, we saw in our particular case that efficient experiments lasted shorter and inefficient ones lasted longer. So this inclination, in this particular case, inclination to invest more in prolonging an unsuccessful experiment was not really fruitful. And most likely reasoning behind investing in something which is not really rational is exactly this principle of commitment and consistency. Of course, I'm not claiming that this principle is not useful always. Sometimes you really have to pursue your idea, but it's important maybe to find some optimum. Another possibility how to analyze when to stop an unsuccessful experiment is doing a predictive analysis after doing data envelopment and after establishing certain experiments as efficient and others as inefficient. So these were some proposals given by Sandra Radovanovic, what could be done. We would need to analyze more data in order to move to the next step, but that's planned. So one example is logistic regression. It's a statistical tool. It basically tells you how, if you increase one parameter by a certain amount, how will this reflect the inefficiency of that experiment. Another example, well, here we tested something, so here on this example, there is the question is about number of researchers, but you can also make a decision tree for the duration of an experiment, of course, and then realize this is just if-then, so this representation of results in a tree form with if-then questions. But of course, again, so in order to do this, you need a lot of data, and this is applied in economics, in organizational sciences, in social epistemology of science. It hasn't been applied yet, as to my knowledge. So I hope that now I convinced you that collecting the data is very useful and constructing these external data repositories. But when we do that, when people do that, they have to be very careful. They have to first consider field-wise organization of these data, because not in every field you will have the same classifications. You can only compare experiments that are similar. You also want this data to be readable. So if they're online in some repository, you want this to be readable. You want this that people can understand what's going on. And you want to only kind of, so this is just the interface. The interface has to compare, has to collect data that are similar, experiments that are similar, and has to represent their data in a readable way. Another point is discussing these parameters. So, for instance, what we discussed is this citation ranking. This is very field dependent. It's clear that we talk about impact factors in one field. In philosophy, impact factor, which is 2, it's extremely high. I don't know whether it exists, right? But in biology, you can aspire impact factors 20 to 50 and so on. So it's very different, right? In some disciplines, impact factors maybe don't even represent maybe don't even play such an important role. That's why you can maybe opt more, what physicists did for this classification, of citation number. But then, also when you do this classification, you have to keep in mind that not in each discipline citation rate is the same. So this is very important. So to conclude, it's timely that these big agencies, or maybe scientists themselves, make these data that they collect and that they have available in some readable fashion, because it can be very useful for making further scientific policies. And what our team, PRSB, here is doing or thinking about, well, one of the important things is all these nice, wavy psychological traps that I presented. They really need to be studied in a scientific context, at least some of them, in order that we can really say that these results are reliable and meaningful for us, right? Another point is to do more case studies in order to have this predictive analysis that I mentioned. Also, we are interested in this funding influence on research, either with actually getting some funding data or this indirectly inferring about it, and making network data envelopment analysis on the data that we have, generating formal models and so on. But because we know when to stop, I will stop here.